Welcome to this course, which is all about autoencoders, and we'll be creating a denoising autoencoder along the way. So in this section, first we are going to see some use cases which will motivate us to learn about this architecture. Next, we will see how autoencoders work, the technical details behind it. Then we will take a look at some of the types of autoencoders. There are a few different variants. Then we'll build a denoising autoencoder using PyTorch, and following that we will train it and we'll test it. Autoencoders motivation. In this video, we are going to take a look at a few use cases, a few problems that can be solved with autoencoders just to motivate us. We'll begin by understanding this term a bit, autoencoder. So auto means by itself and encoder is the act of encoding. So autoencoder by itself encodes data into a certain representation. We'll get into the details later, but this is the essence of it. This can be understood with an analogy. Consider the Morse code, which is a mapping between the English text, the characters, and a series of dots and dashes. Once converted from text to this representation, it can be easily transmitted through telegraph wires. So we are converting a known representation, which is English, into a representation which is a Morse code, which is easy to transfer via wires. Autoencoders do something similar, but instead of a human coming up with the codes, the autoencoder by itself finds out what the hidden representation should be, which is efficient. And we'll define efficient in the upcoming slides. Autoencoders are essentially neural networks with a specific architecture. They can be used for dimensionality reduction, which is extracting essential features from a very high dimensional space into a lower dimension. Compared to PCA, which can only learn a linear relationship, autoencoders can learn complex nonlinear relationships by using nonlinear activation functions. Autoencoders can be used for data compression. Once the high dimensional data is converted to a reduced dimension with essential features, the resultant representation can be treated as a compressed version of the original data. It can later be decompressed with the decoder part of the autoencoder, which will be a lossy version of the original data. But much research is going on to improve the lossy part or reduce the lossiness of the decompressed data. We can generate synthetic data using autoencoders. In this diagram, I've shown a variant of autoencoder called the variational autoencoder, where we learn the mean and the standard deviation of the training data. Once that is learned, then by sampling from the mean and the standard deviation, we can generate newer versions of the same data which has never been seen before. This can be used as a data augmentation technique. We can use autoencoders to remove noise from images, and this is what we'll do exactly in the exercise of this section. We can train an autoencoder to understand or to differentiate signal from noise and efficiently try to remove the noise, giving us the signal which is the original image back. Autoencoders has been used for anomaly detection. So in this case, we train the autoencoder to learn the features of our desired class such that when a non-desired class is presented to it, it will not be able to successfully recreate the non-desired class, leading to a very high reconstruction loss, indicating that it is fake and not the original class that we were looking for. And finally, one more example. Autoencoders has been used to reconstruct a missing portion of an image. This is called a neural inpainting. This can be used, for example, to remove unwanted objects from a photograph. So those were some of the use cases where autoencoders were used to solve the problem. I hope that was motivational.